Simulating carbon capture and storage, or CCS, in En-ROADS. I'm going to show you all the graphs, all the sliders to explore three big questions. How big is this now tiny industry going to grow given a range of assumptions? How much could it address emissions and help the climate? And then third, what does it do to prices for CCS, the amount of pipelines needed, the amount of energy used, the amount of storage that's required? Let's go check this out. First, what are we talking about here? This is industrial equipment that captures carbon dioxide at the end of the smokestack or in industrial processes for electricity production, but also industry. This is like cement and steel and hydrogen and fertilizer that exists around the world at a modest scale. Then pipelines to move it, and then putting it underground, mostly into saline aquifers. What we're simulating here is not carbon capture and utilization. This is carbon capture for what's called enhanced oil recovery, getting more oil out of the ground. We're also not going to be covering carbon capture and storage and direct air capture, or DACs. That's a whole nother video. But there are three types of CCS we're covering here: gas CCS, coal CCS, and bioenergy with CCS, or BECCS. Although this video is going to focus on testing just the gas CCS portion. We'll start with just the simplest way to test CCS. There are two ways to do it, and here are the graphs that you're going to want to look at. On the left, go look at primary energy with CCS by source, and on the right, because we're looking at gas, overall primary energy demand here. This graph shows primary natural gas from fuel, mostly in industry, but also in buildings, and then on top of for electricity generation. Two ways to test it. One is you click on the dots here for natural gas, and you can subsidize it. It needs to be paid for. What is that subsidy? So you could boost a subsidy and see it grow. Here, primary energy with CCS, the blue line grows. And over on the right, we can see that some of the yellow area and some of the darker yellow gets captured by CCS with the gray. So you can see some up here on the top from electric with CCS, and then fuel with CCS over here. Subsidize it, or the other way, I'll undo it. You can also explore it with incentives such as a carbon price, which leads to some CCS getting created, but also overall less gas. You can see how the overall yellow areas shrink because we have a big disincentive to gas. All right, let's dig into one scenario. I'll undo these changes and go back to incentivize gas through a subsidy. I'm going to choose $85 a ton, which is the level of the Inflation Reduction Act in the United States tax incentive for CCS, which is the 45Q, is the part of the tax code. $85 a ton. What if it happened all around the world in this global model? We can see that it grows from very, very small. Way back here, there's very, very little CCS. In fact, today it only exists in Australia, Canada, Netherlands, Norway have sites. Isn't one here at this time in the United States, but it grows about 15% a year very swiftly over time. It's a very big industry growth-wise, and yet over on the right, we can see that not much of the overall natural gas gets captured. Mostly that's because we use so much natural gas around the world, and it takes a long time for this industry to grow. Also, it can't capture much of the CO2 or much of the overall capacity, because it is only applicable to a portion of natural gas usage around the world. It is applicable to about 90% of electricity generation, 80% of industry, but none of the buildings, which is over a third of overall natural gas usage. And it has about an 80% capture rate. You can change many of those assumptions down here under this section of the assumptions. The second big reason it doesn't grow very much, it is very expensive. We go down to financial, we can see cost of fossil CCS. Here it is, a little bit above $85 a ton, which would need to get paid for by either corporations or by governments. And that amount of money would really add up. It could end up being a lot of money. The total cost to capture, store carbon under this scenario passes 30, 40, 50, 60, 70 billion dollars every year just to pay for this. The other thing we notice on the right, see the blue line only partially below the black line. The cost of fossil CCS doesn't drop very much because it has not a very ambitious progress ratio. It is 0.95. You only get a 5% improvement in cost for every doubling of cumulative installed capacity. It doesn't drop very much. That's because it is a high design complexity and high customization needed sort of technology. Those assumptions can be tested and changed here in this area. And it could actually fall faster if it is, say, 0.9, 0.85, but it is unlikely the progress ratio is this low. But you can test other assumptions. Two other interesting factors to check out. One would be the overall transport capacity required, that is related to the pipelines, showing natural gas total pipelines, and then how much is in this scenario. Of course, it could be a lot higher if we had much more CCS. The other would be to see the storage needed. Under carbon removals, we can see how much overall carbon cumulative stored underground. And it could be, of course, a little bit higher relative to the cheapest storage that's available, around 700 gigatons. So we can see that it's staying well below the limit of how much is inexpensive. So the big question we want to ask is, how much will this help emissions and the climate? Over on the left, I'll pull up what's happening with natural gas, and I'm going to undo that carbon price. And over on the right, a very important graph under CO2 emissions is CO2 emitted from gas and captured by CCS. For this test, I'm going to double the subsidy from $85 up to $170 a ton, and we get to see more growth in gas CCS. In the graph on the right, the gray area are the continued emissions from gas. You can see how it's really a lot and hasn't reduced very much. The black line is where it was before any of these changes, and the blue area is how much is being captured by CCS. So overall, we can see that emissions went down a little bit. Did it help temperature? Go to impacts and see that the change is almost negligible. By 2100, instead of 3.3, it's down to what? 3.26, a negligible improvement. What's going on? Well, we get a little less gas emissions of CO2. It crowds out a little bit of coal, which is good. Coal is slightly lower. However, methane goes up just a tiny bit. Why does methane go up? Because we got more gas overall. Look at the bottom right. Natural gas is a little bit higher, the blue line above the black line. Why is that? It's because we made gas cheaper. I'll undo it. This is the marginal cost of electricity production. See the blue line, and I will redo that change. See the blue line going down. Cheaper natural gas leads to more overall gas demand, which means more overall production. So on net, those various factors balance themselves out, including one additional one, which is overall energy use. It takes energy to run the CCS, so we have a little bit of a boost to energy. So overall, in this scenario, there's no real net gain for the climate. And these are the graphs that you would want to look at in order to figure all of that out. This was just about gas, but you can also look at coal CCS. I'll pull up some graphs here. Overall emissions, we can see that we could look at coal CCS under, say, a carbon price, BECS or bioenergy with CCS. We can see the results there. Here's the bioenergy, CCS. Those are the main three types. If you want to see direct air capture CCS, that's in another video. I briefly showed them, but many of the assumptions can be changed under this area: the capture effectiveness, delay times for completing it, progress ratios, the potential in different sectors, and a little bit about how much low-hanging fruit versus high-hanging fruit there is in CCS. And then many of the costs for storage are shared here. All right, there it is, CCS in En-ROADS: gas, coal, and bio-CCS. How big are these industries going to grow? What does it mean for emissions and the climate? And then what are other impacts on storage and pipelines and energy and costs? Go get them, everybody.